Alright, so hey guys. A popular request in my DMs was the 2019 Chemistry Unit 1 paper. So I just decided to, get it done. So let's see what we have here. Of course, there repeats the first question. Alright. Which of the following statements is true about 5 dm cube of hydrogen and 5 dm cube of oxygen at 0 degrees Celsius and 101 kilopascal? All right, this is on the basis of Avogadro's law. Yes, Amadeo Avogadro. Gases of the same volume, temperature, and pressure contain the same amount of molecules, and that's the basis of Avogadro's law. So this says they react to produce 5 dm cube of water. They react completely with each other. They contain the same number of molecules. Okay, that's what we said. Yes. Or they possess the same amount of kinetic energy. Okay, number 1 is C. Let me get rid of this so it doesn't confuse anyone. Yes, so number 1 is C. Number 2 says, which of the following factors is important in determining the stability of an isotope? The neutron to proton ratio. That's where we get the band of stability from. Oh my god, stop doing that. Yeah, that's where we get the band of stability from. Then you have the things and they fall outside of the little band here. Yeah, anyways, that's the neutron to proton ratio. Number 3, which of the following electronic configurations is for the copper 1 ion? That is the Cu plus 1 or 1 plus ion. That means copper generally has the 1 electron in its 4s, and to make it 29, have 1, 2, 3, 4, 5, so that's what, 18, 19, 20, 21, 22, 23, 24. Now they start. Oh my god, when am I going to improve my handwriting? 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Right? Now, when losing electrons, you lose from the 4s first. So you'll lose that one. So you have 3d10. So you'd have the argon core, which with 18 electrons, and then 10 more would give you 28 rather than 29. And the reason, well, you need to remember that chromium and copper, those elements have 1 electron in their 4s because of the half filled and the almost filled or the filled d 3d orbital. All right, let's go down to number 4. The standard enthalpy changes for 2 reactions are as follows. 488. All right, and that's 110 kilojoules per mole. What is the standard enthalpy change in kilojoules for the reaction, right? See here that we started with ferric oxide, that's the Fe3 plus ion, right, with the oxygen and 3 carbons. So here, up here, we started, the equation is the other way around. So seeing that it's the other way around here, we'd have to use the positive value for that. So it's 822 kilojoule per mole plus this here, but we have 3 carbons, so 3 times negative 110 kilojoule per mole. Let's put that in the calculator. 822 plus 3 times negative 110 gives me positive 492, and that is D. Number 4 is D. Great. Alright, number 5 says, which of the following statements are true regarding the factors affecting ionization energies? Alright, number one here, the first option says, an increase in shielding effect decreases the ionization energy. I believe so. An increase in the size of the positive nuclear charge decreases the ionization energy. No. An increase in the size of the positive nuclear charge greater is the pull on the electrons. So there will be more force on the electrons coming towards the nucleus. So number 2, no. Number 3 says an increase in the distance of the electrons to be removed from the nucleus decreases the ionization energy. Yes. So 1 and 3. Number 5 is B. Good. Alright, number 6, I'm going too far. Sodium can form ionic bonds with each of the halides. Which sodium halide is expected to have the highest lattice energy? Sodium fluoride, 6B. I don't know if I should even mention this, but yes, let me say it. Okay, if they just existed here as diatomic molecules like F2, Cl2, Br2, I2, now this would have a greater chlorine, the chlorine molecule will have a greater bond energy as well as lattice energy than fluorine. This is because the fluorine atoms are small. When they're bonded, there will be a great electron repulsion, forcing the fluorine, oh my god, get away. Yes, the fluorine atoms away from each other, so it would require less energy to break the bonds there than for the chlorine. But the trend continues as is as you go down normally after that exception. Did I answer number 6? Yes, I did. Okay, number 7. It asks us which of the following structures correctly illustrates the coordinate bonding between BF3 and NH3. Now, seeing that the nitrogen would be the one with the lone pair of electrons to donate or share, the arrow would have to point from the nitrogen to the boron. So let's look for that. Here we go. Here we have the nitrogen pointing to the arrow there pointing to the boron. So this would best show us the coordinate or dative covalent bond between those two compounds. So number 7 is C. Number 8 asks us which of the following compounds has a giant molecular structure, and with silicon dioxide, here silicon 4 oxide is the same as silicon dioxide. So number 8 is B as in boy. Number 9 says when 86 grams of the ionic salt CaSO4 XH2, that means it has some amount of water with it, is heated so that all of its water of crystallization is driven off, and 68 grams of calcium sulfate remains. The value of X is, that means if 68 grams of calcium sulfate is left from the 86 grams that they started out with the water, that means that 86 grams minus 68 is equal to the amount of water, which is 18 grams of water that was originally there. Now, we need to find out the mole ratio between those. So 18 grams of water is literally 1 mole of water. So 1 mole H2O is there with, let's say, how much would it react with 68 grams? 68 grams. Let's find out how many grams are in 1 mole of calcium sulfate. Calcium is 40 plus 32 plus 30. Wow. Yes, plus 32, because, wait, nope. It would be 32 plus 32 because 2 times 16 is 32. So 4 times 16, that's what we need. Alright, got 136 for 1 mole of calcium sulfate, and we have 68 grams, so 68 over 136 would give us the amount of moles, and it's 0.5, so 0.5 moles CaSO4 with 1 mole of H2O. I should write this properly. I'm so sorry. Stop being lazy. My God, man. Alright, let's do this again. 0.5 moles of CaSO4 with 1 mole of H2O. And we saw where it started out reacting with 1 mole of CaSO4 with an unknown amount of X of water. Whoa, sorry. So 1 mole CaSO4 is equal to some amount of that. If you cross multiply, it have 0.5, X being equal to 1 mole. X would be equal to 0.5 into 1, which is 2. So we have 2 moles of water. Alright, 9 is B, as in boy. Alright, number 10 says the shape of the complex ion is, alright, looking at the coordinate number, it's 6, so it's an octahedral complex. So number 10 is A. Wow. Number 11 asks us which of the following gases is closest to behaving as an ideal gas under the stated conditions. Okay, behavior is closest to an ideal gas is high temperatures. If this happens one more time, God. All right, high temperatures and low pressure. Yeah, pretend that's pressure. So we have H2 gas at 400 degrees Celsius and 1 atmosphere. I believe that's the answer, but let's look at the rest. That's methane at 30 degrees. That's a bit low for the temperature. And here they have the answer is the other way around, like low temperature, high pressure. That's deviation. That's a deviation away from the ideal gas condition. This is ammonia at 400 degrees Celsius. High temperature, yes, but high pressure as well. No, we need low temperature. So 11 is A. Number 12 says the intermolecular forces which are present in ice are hydrogen bonds. Know this. 13. Alright, it says a gas in a syringe occupies a volume of 50 centimeters cube and has a pressure of 0.49 atmospheres. What is the pressure of the gas if the plunger of the syringe is pushed in, reducing the volume of the gas to 20 centimeters cube? Alright, we're told that 1 atmosphere is equal to 101,325 pascals, and we want the answer in pascals. So easiest way to do this is convert atmospheres to pascals. So multiply 0.49 times 101,325, and that should give you the pressure. And now we are relating volume and the pressure, and Boyle's law states that P1 V1 is equal to P2 V2. Alright, so the first pressure that we have was the 0.49 times the 101,325 times the 50 centimeters cube. That's the first volume or initial volume. When we compress it, we got 20, the volume down to 20 centimeter cube, right? And we need to find the pressure, right, when the gas in the gas syringe when the volume is reduced. So we divide P1 over V1 by V2, which is 20 centimeters cube. So the answer that I just said, times 50 over 20, and that gave me 124,000 pascals. Want answer in kilopascals. Oh, I forgot to round it, I'm sorry, but it's 125 kilopascals, because 125,000 pascals is equal to 1 kilopascal over 10 to the 3 pascal. Therefore 125,000 times 10 to the minus 3 kilopascals would be your answer, which is 125. So the answer for 13 is B. Alright, let's go down to 14. Says when magnesium metal reacts with a dilute nitric acid, 0.512 moles of hydrogen gas is produced. The volume that this gas would occupy at 298 Kelvin, that's 25 degrees Celsius, and we're working Kelvin temperature, and 196 kilopascal. Okay, when R is equal to 8.31 joule per Kelvin per mole is, so we're required to find the volume. We're given all of this, so we're going to use this formula. PV is equal to nRT, right? Now the answers here is given in dm cube, but when we find the answer here, we'll be given the answer in meters cubed, because we're using R here as 8.31 and we're using kilopascals or pascals rather than atmosphere, right? If we're using atmosphere for the pressure, you'd know that you'd get your answer in dm cube. So let's see, we're trying to find the volume, so we'll eventually divide by the pressure. So we are told that we have 0.512 moles and 8.31 joules per Kelvin per mole, and we're multiplying that by the temperature, in absolute temperature really, 298. Ensure that it's always in Kelvin, and we're going to divide by 196 times 10 to the, I want this in pascals, 10 to the 3 pascals rather than kilopascals, working in SI units. Why am I calculating? Okay, let's do that. 0.512 times 8.31 multiplied by 298, that's what it says, yes, and divide all of that by 196 times 10 to the 3. Now I got 6.446 times 10 to the minus 3. Let's say that. All right, let me show you. Now that's in meters cubed. So let me clear this a bit to show you how we'd get it to dm now. So I said, what did I say? Yes, 6.46 meter cube is equal, I want it in dm cube, so I'll put the dm on the top. So 10 decimeters is equal, yes, to 1 meter. But we want this thing in cube, so we'd cube all these numbers. 1 cubed and 10 cubed would give you dm cubed, right? So yeah, raise all those numbers to the third power. Meter cube cancel meter cube. 1 cube is equal to 1, so I'd have 6.46 is equal to, sorry, times 10 to the 3, because 10 cubed is 10 to the 3, or 1000, but let's just write it like this to make it a bit more condensed. I forgot something. Oh my god, I am so annoyed with myself. I forgot to put the times 10 to the negative 3. So it's 6.46 times 10 to the negative 3 meters cubed. That's the answer, right? Now, in order to put it in dm cube, now it would be 6.46 times 10 to the minus 3 multiplied by 10 to the 3. These would end up canceling each other and would end up with 6.46 dm cube. So the answer is B for 14. Number 15. Which of the following processes represents oxidation? So can you find this by looking at the oxidation numbers? All right, so this is -2, and the entire compound here has a charge of 0, so you'd have +2 for manganese here, and it's manganese, so it was neither oxidized nor was it reduced, so this does not show oxidation. Now this is MnO4 minus, so this ion here has a charge of -1, so manganese Mn plus -2 times 4 is equal to -1. 2 4s 8 is equal to -1. Mn plus 8 is equal to -1, or lies, it's a -2, so it would be -8. Mn is equal to -1 plus 8, which would give us +7. So in this compound, Mn is +7. And let's clear this so we can work out the other one. Oh my god. Oh my god, yes. This is Mn plus -2 times 4, and it has an overall charge of -2. So Mn plus 2 4 is what? 8 minus 8 again is equal to -2. You bring that over, so Mn is equal to -2 plus 8, and that is 2 minus 8, that's 6, and seeing that 8 is the bigger number, you have a +6, so Mn in this case is +6. Clear and get to the other one. In this case, you see where 7 goes down to 6, so it's not oxidized, but it is reduced. So this does not show oxidation. Now, MnO4 minus, I believe is the same as MnO4 minus up there, so it's plus what? +7. MnO2 minus, we already worked, MnO2, sorry, we already did that, and it's +2. So again, 7 goes down to 2, so it's reduced. seeing that this is the only answer left, this would be the one that would be oxidized, but let's work it out to see. MnO2, we saw where in many cases where we did it before, it has +2, and the MnO4 minus we found to be +7. So you see where the +2 increased to +7, therefore it is the one that is oxidized. So 15 is D. Yes, so let's go down to number 16. It says compounds P, Q, and R form an equilibrium as shown below. Now 2P aqueous and Q aqueous changes to R, 2R aqueous, and it could be reversed. And it says the units for the equilibrium constant Kc are. Alright, so you know that it would be the concentration of R squared, because there's 2R there, over the concentration of P squared times the concentration of Q. The squared is because it's 2P as well. So if you work that out, you would have big M squared, which is molar squared, which is mole per dm cubed squared, over, this is like 3 mole per dm cubed to the 3, because it's squared times 3, 2 times 2, or squared times another is going to give you a third, so it's cubed. This and this leaves with molar, so we're left with 1 over m, which is if we expand it would be 1 over mole per dm cube, which is ultimately dm cube per mole. So the answer for 16 is B. Alright, number 17. Item 17 refers to the following table, which shows the rate results for the reaction A plus B changes to C, and we're given the experiments, concentrations, and the rate of reaction, and we're required to find out what is the overall order of the reaction. Okay, let's find the order with respect to A first. So here and here, B is constant. So we see where this increases from 0.10 to 0.20. So that increases by a factor of 2. So I want to ask myself, 2 to what power makes this rate here increase by 2 as well? Because this is 0.0032 to 0.0064. That's also a factor of 2. So 2 to what power would give me 2, and that's 1. So the reaction is first order with respect to A. Now let's look at B. This here, we have the constant here. It's constant here. So we'll look at experiments 1 and 2 for B. Now we see where it increases by a factor of 2, however the rate does not change, so it is 0 order with respect to B. With that said, the overall reaction would be 1 plus 0, which is 1, so the overall order of the reaction is first order. So 17 is B. Now ammonia is removed from the system, represented by the equation, and here's the equation. It says, which of the following statements about the system is false? Alright, ammonia is removed, Kc remains constant, there is a change in all concentrations, the equilibrium position remains the same. That is not true. The equilibrium reaction will not, equilibrium position will shift in order to restore balance. So if we remove ammonia, the system will shift to the right with my left hand, this is my right. It shifts to the right in order to produce more ammonia. I just said ammonia. So 18 is C. Oh, the rates of both forward and reverse reaction decreases. Okay. Now this says a buffer is made by dissolving 28.8 grams of sodium benzoate. This is C6H5COONA in 1 dm cube of 0.4 mole per dm cube benzoic acid, and the Ka for benzoic acid is 6.4 times 10 to the I'm gonna say that's -5 if my memory serves me correct. That's what it has always been. Let's put -5 mole per dm cube. Now the pH of the buffer is, all right, we're going to use the Henderson-Hasselbalch equation, where the pH is equal to minus log to the base 10 of Ka plus the log to the base 10 of the salt, A minus, over the acid, let's say HX or HA, doesn't matter, it means the same thing, where minus log to the base 10 is pKa. Okay, all right, so first we have to, let's find the number of moles of this thing here. We use 28.8 grams. Now 1 mole of sodium benzoate is equal to 12 times 6, because there's 12 carbons, plus 5 hydrogen, 5 times 1, that's 5 still, plus, oh, there's another carbon, so 12. There are 2 oxygens, so let's say 32, and sodium is 23, so got 144 grams, and we have 28.8, right? And we need to find how many that would be. So would end up with, when cross multiplying, would have 144, n is equal to 28.8, right? To find n, we divide by 144 on both sides. So let's see what we get when we put that in the calculator. So it's 28.8 over 144, and that is 1/5 or 0.2. So we have 0.2 moles. Now let's put that in the calculator, where we have minus log to the base 10 of 6.4 times 10 to the minus 5 plus log to the base 10 of the salt, we had 0.2 moles, over the acid we had 0.4, right? Yes, I got 3.9, and that's here at D. So number 19 is D. All right. It says the solubility product of barium sulfate at 25 degrees Celsius is 1 times 10 to the -10 moles squared per dm to the 6. Now the number of moles of barium sulfate that will dissolve in 1 dm cube of water to form a saturated solution is, find the square root of 1 times 10 to the -10. That's 1 times 10 to the -5. 20 is C. Now 21 says equilibrium is established in the reaction X aqueous plus Y aqueous gives us, or changes to Z or Z aqueous, if the equilibrium concentrations are, the concentration of X is equal to 0.2 mole per dm cube, Y's concentration is 0.3 moles per dm cube and Z is 0.6 mole per dm cube. Which of the following is the value of the equilibrium constant Kc? Kc is equal to the concentration of the products over the concentration of the reactants, or the products of the concentration of the reactants. That's what I said, right? So the product of the concentration of the products over the products of the concentration of the reactants. So in this case, it would be concentration of Z or Z over the concentration of X times the concentration of Y. And in this case, Z is 0.6 mole per dm cube, and this would be 0.3 times 0.2, and mole per dm cube squared, right? So let's get the numbers straight first. 0.6 over 0.3 times 0.2. I got syntax, hold on. 0.2 times 0.3. Okay, I got 10. So the answer is either C or D. Now, seeing that we would have mole per dm cube up here and would have mole squared per dm to the 6 down here, seeing that we're multiplying these twice, like mole per dm cube times mole per dm cube would have mole squared per dm to the -6. So we would be left with per mole dm to the 3 as our answer. Hold on, let me write that out properly, so in case you didn't get it. We would end up with mole per dm cube over mole squared per dm to the -6. Mole cancels that, you'd have 1 mole left down here. This would cancel down here, would have 3 left down here. So because we'd end up with 1 over mole per dm to the -3, when you flip that or find the inverse, it would be mole per mole, dm cube, or dm cube per mole, whichever one you're more comfortable with saying. 21 is D. Now 22, the value of Kc for the equilibrium hydrogen gas and iodine gas is 2HI gas is 860. That's what Kc is at 25 degrees Celsius. It asks us what is the value of Kc at 25 degrees Celsius for the following equilibrium. Now we're seeing where everything is halved. So to find the Kc for that, using the Kc above, would find the square root of Kc when we got 2 moles of HI. So the square root of 860 is 2 root 215, which is 29. So the answer for 22 is 29. Wow. '23, the reason why we found the square root is because this HI here, remember that when we're finding Kc, would square it, right? So down here would basically be raising HI now to the power of a half, which is really the square root of the concentration of HI over the square root of the concentration. Oh my god, I really should invest in a bit more space for these things. All right, let's try this. We would really be finding the square root of the concentration of HI over the square root of the concentration of H times the concentration of I, which would ultimately give us the square root of everything here. And seeing that originally the concentration of HI over the concentration of H times I was 860, to find the answer here, this would basically be the square root of 860, and that's where we got 29. Hope that was clear. Oh my. 23. The expression for the solubility product KSP of lead iodide is, no, lead iodide I believe is PbI2. If that dissociates, you know, we're gonna have Pb2 plus, right? Yes, Pb2 plus, and iodine is I minus, but we'd have two of those, seeing that we have that over. So the charges would balance, because now you'd have 2 minus plus 2 plus, and that's 0, and over here we already have 0. All right, the solubility product would be the concentration now of Pb2 plus times the concentration of I minus squared, because we have the 2 here. So let's look for that. Now the square is right here, so that's not it. This is what I wrote down, I believe. B, 23. Yes, but let's look at others. Again, this makes it incorrect, and this here, the 2 plus there, makes it incorrect. Ultimately, the 2 here makes that incorrect. So the answer is B for 23. 24, it's like the same thing, right? The basic same principle. Which of the following expressions represents the solubility product of iron 3 hydroxide? So if we have Fe bracket OH bracket 3, so we'll have Fe3 plus the OH minus ion, but 3 of those, because we have 3 here. Again, charge is balanced, so you know your equation is balanced. Also, we have the same amount of species on both sides, so that's also a way you can see that your equation is balanced. Now, the solubility product would be Fe3 plus multiply by the concentration of the OH minus ion to the 3rd power, because we have 2 here, the number 3. So we're looking for this. Oh my god. Okay, Fe3 plus, I believe that's what A says. So 24 is A. Let's see why the others couldn't be. No. Again, they put the 3 here, they put the 3 here. So that's what's kind of making it not work. But the 3 here is correct, but we can't use it because the 3 is here as well. So D and C is incorrect. So let's move on. 25. 25 refers to the following diagrams for the reaction P plus Q plus R. So, alright, here it's a rate versus concentration. So the order with respect to P is first order here, second order. Now the fact that rate times Q square here gives us a line which is directly proportional, tells us that this is in second order. Yep, and seeing that the rate doesn't change, it's a 0 here with respect to R. So the rate equation is R is equal to K P to the 1, which is P, and Q to the what? 2, or Q squared. let's see why r is not in the equation. R to the 0 is equal to 1. Any number to 0 is equal to 1. So basically, if we add 1 there, it's not really doing anything but holding a place. So it's not really necessary. But yeah. Let's see, 26. The weak acid HX dissociates as follows. The dissociation constant Ka for the reaction is 1.0 times 10 to the negative 12 mole per dm cube. Now, what will be the approximate pH of 1.0 times 10 to the minus 2 mole per dm cube of HX? So multiply this number here by Ka, then that would give you the H plus ions squared. So in order to find the concentration of the H plus ions, you will find the square root of that 1.0 times 10 to the minus 2 times multiply by 1.0 times 10 to the minus 12. Once you do that, square root of 1.0 times 10 to the minus 2 times 1.0 times 10 to the minus 12, I got 1 times 10 to the minus 7. Now pH is equal to minus log to the base 10 of the concentration of the H plus ions. Now looking at this, I can tell that it's 7 because minus log to the base 10 of 1 times 10 to the minus 7 is 7, but you can put it in the calculator to just be sure. I am sure though. So the answer is 7. 26C. That's where we are, right? 26, yes. Now 27 says precipitation of a sparingly soluble salt occurs on addition of a common ion only if the ionic product is greater than the KSP. 27 is D. 28, the activation energy of a reaction is unaffected by a catalyst, is affected by temperatures, is an energy barrier to the reaction or reduces the speed of the reactant molecules. So it is an energy barrier to the reaction. 28C. Alright, marine animals such as oysters and other shellfish rely on the slow precipitation of calcium carbonate to form their shells. Which of the following properties helps this process? So it's greater ionic product of Ca2+ and the CO3 2- smaller solubility product or greater solubility product. So alright, 2 and 3 cannot be together, so it's either 1 and 2 or 1 and 3. Now greater ionic product of Ca2+ and CO3 2-. Now if the alright, let's go back up here. 27 is true. If the ionic product has to be greater than the KSP, then you'd need a smaller solubility product with a greater ionic product. So 1 and 2 for 29, so that makes 29's answer C. How I think about it is if the solubility product is great, that means that it is very soluble, but if it is small, it's not very soluble. And I think that's how it's supposed to be thought about anyways. So 30, the standard electrode potential of tin is that with the E0 value being equal to minus 0.14 volts. Yes, so would be cathode. Oh my god. Cathode minus anode, which is the more negative. That's how I think about it. More negative electrode. And here we see that the tin is being reduced. So that's the cathode. So the tin is always going to be in front here when we're trying to solve our E0 value. So we have minus 0.14 volts, and we're going to subtract the other E0 values. So let's just put E0 values so I don't have to, rewrite that. And it says, in which of the following equations is the metal unable to reduce tin? Now, if we put minus 0.14 minus 2.38, let me write that in case you didn't get it how I said it. Let's say minus 0.14 minus 2.38. That gives me 2.24. Now, seeing that E0 value is positive, that means that the equation would be feasible, or the reaction would be feasible. Therefore, magnesium metal will be able to reduce the tin metal. Now let's try the other E0 value. Minus 0.14 is the same principle. Minus negative 0.44. That gives me 0.3. It is a positive E0 value. Therefore, the reaction is feasible. Iron metal will be able to reduce the tin metal. Let's try the other one, negative 0.14 minus negative 0.76. I got 0.62. Therefore, it is feasible. Zinc will be able to reduce the tin metal. Let's try the last one, minus 0.14 minus negative 0.13. I got negative 0.01. Now this would be the answer D. It's not feasible. Lead will not be able to reduce the tin metal. Kind of makes sense too. 31. Which of the following transition elements has an unpaired electron in its s orbital? As I said, chromium and copper. Those two elements have unpaired electrons an unpaired electron in their s orbital. So 32, which of the following chlorides of the group 4 elements is the best electrical conductor? The one that shows the most ionic properties. So A, lead tetrachloride for 32. 33, which of the following ions has the greatest polarizing power? Greatest polarizing power would be the most, in this case, the most electronegative. So the furthest to the top of the periodic table and the furthest to the right. So first, let's look at the elements. We have ions, but let's look at the elements. We have strontium, calcium, lithium, beryllium. Now we have these here being in group 2, these in group 1. hold on. Okay, yes, I got it now. So this is group 2, group 1. Now both beryllium and lithium are way above calcium and strontium, right? So these would be more electronegative. Now I am talking foolishness. Beryllium is not a group 1 element, it is a group 2. So it would be the one furthest over. So lithium group 1, so it would be one of these group 2. So now beryllium is furthest to the top, because from bottom to top you would have strontium, then calcium, then beryllium. So the answer for this is D, beryllium, or yes, the beryllium 2 plus ion. Yes. Oh my god. Group 1, these are group 2. Group 2 is further over to the right, and then beryllium is furthest to the top. So that about covers that. Let's go down to 34. Says HCl, HBr, and HI gases are produced when solid samples of NaCl, NaBr, and NaI respectively are treated with concentrated sulfuric acid. Which of these gases will undergo oxidation? Brr. Alright, first of all, this is like a general thing, like sulfuric acid is not a good enough oxidizer or not good enough to oxidize, the fluorine and chlorine hydrides. Would that be how I say it? It wouldn't be good enough to oxidize these, so it would not HF and HCl, if these were, if HF was a part of the question, would not undergo oxidation. However, HBr and HI would. I think this is supposed to be in our books. I read it in a textbook. Then again, I don't know. Yes, so the answer for 34 is C. Let's go down to 35. Says which of the following oxides of elements in period 3 are correctly matched with their acid-base character. Now we have aluminum oxide, which we know is both acidic and basic. So I don't think this would be suitable, or it's not entirely correct, but yes, sodium oxide is basic and the phosphorus 4 oxide is acidic. So 2 and 3. Yes, aluminum oxide is not entirely basic, but it does showcase acidic properties. 36 refers to the following information. Now we're trying to find the X2 plus ion, or we need to know what the ion is. We don't know what it is, and when put in aqueous sodium hydroxide, white precipitate soluble in excess is formed. When it's in ammonia, white precipitate insoluble in excess is formed. Right, so it says which of the following reagents does not aid in the identification of the X2 plus ion? Nitric acid, because all nitrates are soluble. So we still wouldn't know, even if what the X2 plus ion was, if we had put or added nitric acid, because the X2 plus salt of X2 plus nitrate, of that X2 plus ion would form, and it would be soluble in both. In that case, we still wouldn't know what it was. Now 37 says, which of the following statements about oxides of the element in period 3, sodium to chlorine, is not true? Now the oxides react with water to form alkaline solutions. The oxidation number of the elements in the oxide increases across the period. Yup. Across the period, the oxides change from basic to amphoteric to acidic. Yes. The structure of the oxide changes from giant ionic to simple covalent. Very much so. A is the answer for 37. Let's go back now to 38. Which of the following statements about bromine is correct? It is red-brown in color. Yes. It is denser than chlorine. Yes. Chlorine is a gas. Bromine is a liquid at room temperature. It is a gas at room temperature and pressure. No. 1 and 2. 38 is A. Yep. 39. Which of the following elements gives a green flame when heated? Copper. Magnesium gives a white flame. Sometimes copper gives a blue. Sometimes they say blue-green. Calcium and sodium. Calcium gives a reddish flame, and strontium as well. Lithium as well. And sodium gives a yellow flame. I think they say sometimes it's red, but they just say standard yellow. Which of the following elements in the table can be classified as a transition or a transition element? Element 1, the one with the highest melting point and density. So high density and high melting point, or very high melting point. So 40 is A, 1 only. Yup. Now 41 refers to the following graph showing the first ionization energy, i.e. of some elements. Now the sharp increase from copper to zinc is caused by a filled 4s orbital. Remember that copper only has 1 electron in its 4s. So when you get to zinc, it now has the two the 2 electrons in its 4s. 42. Which of the following properties belong to group 2 elements on the periodic table? Group 2 elements are metals, so yes, they have high melting points. Wouldn't say low density. Low melting points, no. Poor conductivity, no. They're metals, so they have high conductivity. Low densities, no. Poor electrical conductivity, no. Alright, high melting points and high electrical conductivities. 42D. There we go. 42D. Now 43. Which elements can be classified by their response to externally applied magnetic fields as diamagnetic, paramagnetic, and non-magnetic? Which of the following elements is considered to have a high degree of paramagnetism? It would be the one with the most unpaired electrons. So calcium would have the argon core, and then would have a 4s2, no unpaired there. For cobalt, that's 27 electrons. Argon would be 18, 4s2. Oh my god, 4s2 would give you 20, and we need 7. So 1, 2, 3, 4, 5, 6, 7, and we have 3 unpaired electrons. And now scandium is 21. So again we have what? Argon core, which is 18, 4s2, which give us 20, and 1 unpaired electron, so that's not it either. because here we had 3 unpaired, so that would be 1 is less than the 3 unpaired. So still we have cobalt here having the most paired, and the zinc has a full 3D orbital and 4s, so that wouldn't be it either. So the answer 43B. Great. Let's go down to 44, then 45, and see what we have. All right, the ionic equation for the formation of chromium hydroxide from chromium 3 sulfate and the dilute ammonia is, all right, is, all right, chromium 3 aqueous, yes, OH, but this isn't the formula for this. It would be CrOH bracket 3. That's what we're looking for on the product side. So this is correct, but this wouldn't be solid either, so that's not it. Chromium 3 plus aqueous. Why is this here? That's not it. And we're here at D. Yes, aqueous. Now 3 OH in order to balance it, and that is it. 44D. Now, what deduction can be made from the following reactions of iodine and chlorine with sodium thiosulfate? Alright, knowing about the trends, I know the answer is A, because chlorine is a stronger oxidizing agent than iodine, but let's prove it based on the equations here. Alright, so sulfur in this equation has a oxidation or an oxidation number of, let's see, 2s plus minus 2 times 3 is equal to minus 2. 2, 3 is 6. I have minus 6 plus, nope, yep, minus 2s minus 6 is equal to minus 2, and bring over the 6, so we have 2s is equal to minus 2 plus 6. 2 from 6 is 4, because 6 is larger, 4 is positive here. 2s divide by 2 on both sides. My voice is starting to crack again. S is equal to plus 2, and seeing that it's the same thing down here, just put it, don't have to work it out again. Now let's look at the oxidation states for sulfur in on the product side. Let's see what we're dealing with. Hurry up and come on. Alright, now we have 4s, right, plus minus 2 times 6 is equal to minus 2. 2, 6 is 12, so I have minus 12 there, and 4s here is equal to minus 2 plus 12, because we add 12 to both sides. 4s is equal to 10, so 4 into 10, 2 4 is 8, and leave 2 over 4, so 8 and 2 over, whoa, 2 and 2 over 4, which is 2.5. 2.5, right? Now let's look at sulfur in the equation with chlorine. Wow, we have it right here. We have s plus 2, or minus 2, sorry, times 4 is equal to minus 2, 2 4 is 8, minus 8 is that, minus 2, S is equal to 8 minus 2, that's 6, right? Yes, it's 6. Took you a while though, bro. And we see where S is plus 6. So you see that there's an increase from 2 here greater than here, because this is from 2 to 6 and this is 2 to just 2.5. So there's just an increase of 0.5, and the increases here is about like 4. So chlorine is a stronger oxidizing agent than iodine. And I guess that's it for the 2019 paper. Guys, thank you for watching. Again, if you're hearing this, that means you've made it to the end of the video. Congratulations. You know what to do. Like, subscribe, go follow me on Instagram on both my business and the main page. Yes, and I answer my DMs, so you can DM me. So that's it, and I'm mad tired, so bye-bye.
Come and fly away with me. Come and fly away.